This is going to be a crash course on tensors. So I'm going to try and speak clearly here. I'm at relatively slow speed as well. Let's see, how do I go page down? Does that work? Okay, I can just scroll like this. So, first question, what is a tensor? So, we're going to review vectors and vector spaces. So, remind yourself what a vector space V over the real numbers is. Remember that the vector space is this place where we can add vectors and we can scale them, and there's all kinds of associativity properties and commutativity properties and all of these kinds of things. Definitely needs to be reviewed. So here, yes, they can be added and also scaled. Now, when dealing with vector spaces, in particular finite dimension ones, if I have a vector space here, V, let's say V is our vector space, and the dimension of V is, say, n, then if I take any V in our vector space, then it can be represented as this sum of its basis elements, right, as I've shown here. And the important point here is that, as I say here, it depends on the choice of basis, okay? So a good example of that is if I have my R2 here, actually I can draw a straight line here. Oh, never mind, I can't, that's only in the full version, that's fine. I can draw myself a little plane here, so here's R2, and the standard basis is this E1 and E2. And then if I take a vector, say for instance this one, this guy can be written as 2E1 plus 1E2. In other words, its components are 2, 1. But on the other hand, if I take these as my basis vectors, not sure if the yellow is so easy to see, but if this is E1 and this is E2, then this same vector, V, right, now V, sorry, I'll call these E1 prime and E2 prime. Now V is equal to, well, it's actually going to be negative 2 E1 prime minus 1 E2 prime, right? In other words, its components are minus 2, minus 1. So the vector is the same in both circumstances, but its basis elements, its components, are different. And that's important. That's going to come up later. Okay? So that's just a review on that. Okay, so now we're going to talk about the dual space. So the dual space of V is the set of all linear maps from V to R. Okay, so here are our key terms. Oops. Linear maps from V to R. Okay, and it's denoted with this little star here, right? So it's the set of all these omegas that go from V to R such that omega is linear. Now, this is an important point, okay? This is actually not that hard to show. It's also a vector space, okay? And because it's a vector space with the same dimension as V, we can give it a basis, which is typically given this notation with the raised indices, okay? The canonical basis, the one we usually take, is the one that, so, all right, let's backtrack, right? So we know that omega here, any covector, is a linear map, right? So if I take omega of V, so omega, this guy is a covector, and this guy is a vector, we know that that's going to be equal to some real number. Okay? Now, the basis of our vector space was these guys, E1, En. Okay? And we want to define a basis of the dual space, E raised 1, E raised n. But there are multiple choices for our basis. I mean, as you saw with R2, there was this basis, but there was also this basis. You know, so there's multiple different choices of bases. So we have to decide what's the best basis to choose, and it's actually this one, this canonical basis. This is the best choice. Okay, this makes the calculations the easiest. Okay, so EI, so the ith basis vector in the dual space, okay, this is a member of the dual space. This is a member of the original space. So the ith basis element in the dual space acting on the jth basis element in the original space gives us delta ij. And as a refresher, delta ij for integer ij is 1 if I equals j, and 0 if I is not equal to j. Okay? And as I've shown here, elements of the dual space are called covectors. Okay? And this other important point is duality. Okay? V star is the dual of V. But V is also the dual of V star. So the original space is the dual of itself, right? So we have, let's say, dual of V equals V star. So dual of V star, well, we know that when we take the dual of something, we just add a star, is V star star, which is equal to V. Another way of saying that is that the dual is an endomorphism, but that's, you know, whatever. That's just technical terminology. The dual of the dual is the original space. Okay? So that's pretty neat. I'll clear that. Oops. All right. Now, we can visualize it quite nicely. So we typically view vectors in a vector space as column vectors, right? So if we have some abstract vector space V, all right, and we have some element of that, right? And we've, say, chosen some basis, right? So we've chosen a basis. So that's our E1 all the way up to En. Okay, then if we can represent V as this linear combination, then what we typically do is we write V as this column vector, V1 all the way up to Vn. All right, so for example, 1 E1 plus 3 E2 is equal to this column vector 1, 3. Okay? So vectors are column vectors. Okay? We view covectors as row vectors. Okay? And here's how we view their interaction. Okay, so we know that the covector acting on the vector gives us a real number, but because of the duality, the covector on the vector is the same as acting the vector on the covector. And this is typically written using a dot. Okay, and we can visualize it using matrix multiplication. So this is a 1 by n matrix, or array, whatever you want to call it. Let's call it an array because I don't want to confuse it. Eraser. There we go. Let's call it an array because I don't want to confuse it with matrices later. And this is a n by 1 array. And if you remember from your basic linear algebra, when you take let's say n times k array with a k times m array, you get a n times m array. So here we should be getting a 1 times 1 array, which is just a number, as expected. And I'm sure you remember from your linear algebra course that it's this one times this one plus this one times this one, so it's omega 1 V1 plus omega 2 V2, which is this sum, and that's a real number because we said all the entries were real. Okay. Let's clear this. So the next level of abstraction is matrices. So, right, we have a scalar, which is just a real number, okay? We have a vector, which is a map from the dual space, which is a map from the dual space to the real numbers, and we have a covector, which is a map from the original vector space to the real numbers. So we can basically put the vector and the covector together, and we can say that a matrix is a map from one copy of the dual space and one copy of the original space to the real numbers. Okay? And as in the previous slide, hang on a second. You left multiply with the covector and right multiply with the vector. So we do the same here, and we stick the matrix in the middle, and you can use your matrix multiplication again. Multiply this guy in here, you get this, and then multiply that through, and you get this sum right here. All of these things are real, and so this is a real number. And you can check the linearity and so on and so forth fairly easily as well, right? So let's review, right? So we have so the covector, so the vector, all right, that took in, I think this is too small. oh, that's too big. God damn it. So the vector, okay, took in one copy of the dual space. The covector took in one copy of the original space, and the matrix takes in a copy of both. I'm actually going to move that over. And the matrix took a copy of both, right? So I've combined copies of the original, of the dual space and the original. So what do? In mathematics, we generalize, right? So I took in one copy of the original space, or the dual space, and one copy of the original space, but I can take in as many copies as I want. Okay, so here we go. A PQ tensor. A PQ tensor is a multilinear map. So what do I mean by multilinear? Well, it basically just means linear in a lot of dimensions. So the vector, right, the vector here, or let's say the covector takes in one vector, okay, and linearity in this case meant that, you know, omega of lambda v is equal to lambda omega of v, right? And omega of u plus v is omega of u plus omega of v, right? And then, of course, the matrix, so the omega was linear in its first argument, all right? And the matrix, so this was our covector, all right? And then our matrix, all right, matrix was linear in both its arguments. So you could say it's bilinear, right? So multilinear just means linear in a lot of arguments, right? Linear. That's all that multilinear means, okay? So a PQ tensor is a multilinear map that takes in P covectors and Q vectors and outputs a real number, right? So here we have the P, oops, here we have the P, here we have the Q, right, and it outputs a real number, okay? So the components of the tensor with respect to a given basis are just what you get when you act it on the basis vectors, right? Now this might seem like a strange equation, but it's actually quite simple, okay? And I'll demonstrate. If I have a matrix, let's actually start with a vector, okay? If I have a vector here, which is v1 and v2, okay, how do I get its first basis element? Well, I can actually compute v of e1, okay, which is this guy, and then using our matrix multiplication, this is just v1 plus, so let's be more explicit, 1 times v1 plus 0 times v2, right? This guy here, this guy here, this guy here, this guy here, okay? And that, of course, is just v1. Okay, so V of E1 is V1. All right, so similarly, you can generalize this up. Okay, so if I have a matrix here, okay, M11, M12, M21, M22. If I want to get M21, right, I need to calculate M of, let's see here, E2, E1. Okay, so this is going to be 0, 2, or sorry, not 2, my bad, 0, 1, and 1, 0. Okay, and this is going to be 0, 1. Why did I write a comma? 0, 1 times this vector here. Okay, 1, 0, 1, 0, M1, 1, M2, 1. Okay, and then this is just going to be M2, 1. So M of E2, E1 is M2, 1, right? So I'm just generalizing this up, right? So that's how you get the basis elements. And again, the basis elements are going to depend on what your choice of basis are. Okay, so that's what a tensor is. Really not that complicated. So how to manipulate tensors? So this guy right here, Einstein summation notation, is going to be your best friend, really. Because when you're dealing with all these indices, you know what I mean? If you're contracting on like 3 indices and trying to write a summation over 3 indexes, it's just brutal. So we do this summation notation, okay? So a repeated up and down index implies summation, okay? So for instance this, right? So this is not true with repeated down indices. So MII, okay, is not M11 plus M22 plus ... Okay? The way we would write that, okay, is we would actually write, let's see, we would actually write delta I, let's see, delta ij, yes, delta ij, mij, okay, because this delta is only 1 when I is equal to j. So we would write it like this, okay, not like this, okay. Let's erase that. So repeated repeated up and down, okay, they have to be up and down, all right. And, you know, for instance, this is just a really neat way of writing the trace of a matrix, right? So what was a matrix again? So a matrix was a 1-1 tensor, right? Because it takes in 1 covector and 1 vector, right? So it has 1 up and 1 down index, and I can sum over them. I can sum the diagonal elements, and that in linear algebra is called the trace. I can take the dot product here, U1, V1, all the way in UN, Vn, that's just the dot product. And I can perform contractions on more than 1 index at a time. A11, B11 plus A12, B12 plus A21, B21, all the way up, you know, all of those things right there. Okay, so Einstein summation is really good. Allows us to be very compact with our notation. Algebra with tensors. So much in the same way that you can scale vectors to get a new vector, you can scale a tensor, right? So I can have some, let's say, 2-0 tensor. So I have a 2-0 tensor, so that's represented with a vector of vectors basically. So let's say I have 1, 0, minus 1, 3, right? And I can scale that. I can multiply it by 2, and that's just going to move into the entry. So 2, 0, minus 2, 6. Okay, you can do that. All right, you can add tensors, but you can only add them if they're the same shape. Okay, so can't add a 1, 1 tensor to a 2, 0 tensor. All right, they're elements of different spaces. They can't be added like that. Okay. Oh, I forgot to mention just a bit of terminology. Sorry, I'm backtracking. Okay, but when you have a PQ tensor, okay, when you have a PQ tensor, okay, the rank or order, both terms are used, is P plus Q. All right, so that's just a bit of terminology there. And what I'm saying here, what I'm saying here is that you can only add tensors if they're the same shape, right? So you can't, that's too thick, you can't add a 1, 1 and a 2, 0, even though they have the same rank, they're a different shape. And so you can't add them. Okay? You can contract. Okay? So scaling a tensor gives you a tensor. Adding a tensor gives you a tensor. You can also contract. If A is a tensor and B is a tensor, let's say this is a 0, 1 tensor and this is a 2, 0 tensor, okay? Then the tensor, let's call it C, which has upper index J, which is equal to let's be consistent, Ci, which is equal to AJ, BIJ, summing over the J's, of course. This guy is also a tensor, and it has shape 1, 0, because it has 1 up index. Okay, so contracting a tensor of rank M with a tensor of rank N yields a new tensor of rank M plus N minus 2. So in our case, we had this as 1, and we had this as 2. So 1 plus 2 minus 2 equals 1, which is the same as the rank here. Okay. We can also do tensor products. Okay. So for instance, if I have V being a 1, 0 tensor with components, let's say A and B, and I have omega is a 0, 1 tensor with components C and D, okay, then I can construct V tensor product, it's this symbol right here, omega, okay, and that's going to be a 1, 1 tensor, right, because V was a 1, 0, and omega was a 0, 1, and using this rule here, their tensor product is going to be a 1, 1, okay, and we know a 1, 1 tensor is a matrix, and all we do is we just multiply the components. So V tensor product omega, the 1, 1 entry of that is V1 omega 1, so that's AC. The 1, 2 entry is AD. The 2, 1 entry is BC. And the 2, 2 entry is BD. Okay, so that's an example of how you can do tensor products. Okay, And then, of course, I've written it in the general form here. Okay, so in our instance, right, we had V times, sorry, this was sloppy. Where was I? Right, so we had V tensor product omega 1, 1 is equal to V1 omega 1. Okay, that's pretty much that. Okay, now, I'm getting long. I'm getting over 30 minutes here, so I'm going to try and wrap it up in the next 10 minutes, so sorry about the length. Transforming tensors. So as I said, the components of the tensor depend on what coordinate system or basis, they're kind of the same thing, what system you use, okay? So how do the tensor components transform under these change of coordinate systems, okay? So, basically, scalars don't have components because they're rank 0 tensors, so they don't transform. Vectors, okay, they transform this way. So they transform with the bar on the top, right? So I should probably be more clear about this. So our original coordinates were this x1 all the way up to xn, and our new coordinates are the barred coordinates, so x bar 1, x bar n, okay? So we want to transform our tensor with our original components to its barred components, right? So vectors transform this way with the bar on top. Covectors transform with the bar on the bottom, okay? And tensors basically transform, you just stick p copies of the vector transformation law times q copies of the covector transformation law, and you contract that with the original tensor, right? So a very quick example of that is if we come back to R2, okay, we have, this is our x and our y. They have the basis vectors e, let's go, let's be consistent. So this is x1 and this is x2. This is E1 direction, E2, okay? And I'm going to define a new coordinates, okay? So x bar 1, okay, is going to be equal to, let's say, 1/2 x1 plus x2. X bar 2 is 1/2 x1 minus x2, okay? So if we have the matrix 1, 2, 3, 4, these components with respect to our original coordinate system, what's it going to transform to? Okay, well, let's do it here. So we'll call this guy M. Okay, M is a matrix. It's a 1, 1 tensor, right? So M bar 1, 1 is going to be, okay, first one, all right, we're going to have dx bar 1 dxi, all right, and then dx j dx bar 1, which is going to be, okay, dx bar 1 with respect to dxi, sorry, it should be m I j. Well, okay, and it's probably a lengthy calculation, but in principle I can invert these as well, so I can have, these guys in terms of the other coordinates, g x bar 1, x bar 2, and I can invert these and I can work out what these other derivatives are and do the summation and work it out. But I don't have enough time to do it right now. Okay, but the point is, they transform like this. And side note, this is actually the physics definition. So when you deal with physicists, they just say a tensor is anything that transforms like a tensor. And this, while kind of true, is a pretty shit definition. Because it really doesn't tell you what a tensor actually is. Okay? So that's what I'm trying to demystify right here. Okay? But formally speaking, yes, a tensor is anything that transforms like a tensor. Okay? Last thing is tensor calculus. Basically, tensor calculus is really hard and far too complex a topic for me to fit into a, well, not even a short video because we're approaching 40 minutes long. So yeah, you're going to need to study some differential geometry. Okay. So wrapping it all up, let's talk about some applications and examples. So these are some applications, right? Okay, this guy right here is called the tidal tensor. Okay, this this helps us, so tidal tensor helps us work out gravitational field non-uniformity. Okay, Faraday tensor, the electromagnetic tensor, allows us to formulate Maxwell equations in a coordinate invariant way, right? So as I said, because these tensors have this transformation law, right, basically it allows us to be fluid with our coordinate system, because once we know something is true in one coordinate system, we can just transform it into a different one. Okay, so this is really useful. Okay, and that's basically what the purpose of this is. We have the angular momentum tensor. Okay, this guy right here. Oops. This guy right here is called the Levi-Civita tensor. Okay, and this is just the angular momentum vector. Okay, so this is our angular momentum tensor. That's useful in applications. We have the Cauchy stress tensor, which we're obviously covering in fluids, right? So we have this isotropic part, and we have this deviatoric part. Okay. There's this torsion tensor. So this basically allows us to test if a coordinate system is good in a certain sense. All right. And finally, we have this beast, the Riemann curvature tensor. Basically helps to formulate the curvature of space-time. Okay, so basically tells us how curved space-time is, which is going to be very relevant for calculations. And of course, there is many more. Many more. Okay, but that's a flavor. So I hope this was a, not brief, I'm not going to say brief, but I hope this was a useful introduction. Yeah, that's it. So signing out.